Now we start with an introduction to impact evaluation. Impact evaluation is a study that attempts to measure the causal impact of a project, program, or policy on an outcome of interest for governments and other interested parties. And it's about answering two questions. How do you choose between competing programs when resources are limited, so cost versus benefits, and how do you ascertain the benefits? Does it work? Is there a causal impact of the program? We can usually measure outcomes of interest for people who participate in the project or program or are affected by the policy. The hard part is measuring what their outcomes would have been if they didn't participate, and this is called the counterfactual outcome. So now we take a look at the evaluation problem. What is the causal impact of the program, project, or policy on the outcomes of interest? So Y is the outcome of interest, and for each individual, there are two potential outcomes. Y0, which is the outcome without the treatment, and Y1, which is the outcome with the treatment. Both Y0 and Y1 are defined for all people, and you want to estimate the gain from the treatment, so the difference between Y1 and Y0. But since only one outcome is observed per individual, the difference is unobservable, creating a missing data problem. The observed outcome Y depends on the participation P. If P is equal to 1, the individual participated or is treated, therefore Y would equal to Y1. If P is equal to 0, the individual didn't participate or is not treated, therefore Y would equal to Y0. And so Y, the outcome of interest, is equal to P multiplied by Y1 plus 1 minus P multiplied by Y0. So if P is equal to 0, then Y will also be equal to 0 and vice versa. And so establishing causality is hard due to the inability to observe both Y0 and Y1 simultaneously. Now in terms of the parameters of interest, we have the average treatment effect, ATE, and this is the mean impact of a program across the entire population, whether treated or not. And so the ATE is equal to the expected value of Y1 minus Y0. And then we have the average impact of the treatment on the treated, ATT. This is the mean impact of a program specifically for program participants, so where P is equal to 1. And so the ATT is equal to the expected value of Y1 minus Y0 given that P is equal to 1. And then we have the conditional ATE, or the conditional average treatment effect, or CATE. This is the mean impact of a program for a subgroup, for example gender. And then we have other parameters like the ATEX and the ATTX. These estimate effects conditional on observable characteristics, for example age or income. So the ATEX would equal to the expected value of Y1 minus Y0 given X. So it's the general population which is treated or untreated with a certain X trait or characteristic. And then we have the ATTX, and this is the expected value of Y1 minus Y0 given that P is equal to 1 and given X, so it's treated individual with a particular characteristic or trait. And so in an example, when calculating the ATT, we get the sum of the difference between Y1 and Y0, and we divide it by 4 for the 4 people who were treated. And then when calculating the average treatment effect, we get the sum of the difference between Y1 and Y0 for everyone, regardless of whether or not they were treated. And then when calculating the conditional average treatment effect for men, we get the sum of the difference between Y1 and Y0 only for the men, and we divide it by the 4 men in the sample. And this is whether or not they were treated. Now let's talk a bit about internal and external validity. Now internal validity is the ability to confirm that an observed correlation between a program and outcomes reflect a true causal relationship. And it's achieved by controlling the environment and ensuring a valid comparison group, for example lab experiments. But then the common threats to internal validity is systematic differences between the treatment or control groups, for example selection bias. So the analyst should prove the two groups would have had identical outcomes in the absence of the treatment. The other threat is concurrent third factors influencing both the treatment and outcomes. For example, external policies or events happening at the same time as your intervention. And then external validity is the extent to which your causal findings can be generalized to other populations, settings, or times. Let's take a look at the trade-off between internal and external validity. Well, strong internal validity, for example lab or field experiments, often sacrifices real-world applicability. And then strong external validity, for example, observational data or natural experiments, may lack controlled conditions, risking causal ambiguity. Now let's take a look at experimental and observational methods. So lab experiments are conducted in highly controlled environments where the researcher controls all factors except the intervention. Here there is strong internal validity due to strict control, but there's weak external validity due to the artificial setting that may not reflect real-world conditions. And then we have field experiments, which are often RCTs, Randomized Controlled Trials. These are conducted in real-world settings with random assignment to treatment or control groups. These have strong internal validity because randomization reduces bias, and they have moderate to strong external validity. It's more realistic than lab settings but may face compliance issues. And then we have natural experiments. These leverage exogenous or external events, for example policy changes, errors, etc., to create treatment or control groups. These have potentially strong internal validity if variation is truly random, and strong external validity due to real-world context. And then we have observational data, for example surveys. These analyze naturally occurring data without researcher intervention. Internal validity is weak. We have the risk of confounding factors, but the external validity is strong, but data reflects real-world diversity. So in terms of use case examples, lab experiments could be used for testing psychological theories in control settings. Field RCTs could be for evaluating a new teaching method in schools. And natural experiments could be studying the impact of a sudden policy change. And observational data could be analyzing census data to infer health trends. Now we move on to the randomized controlled trial approach. So RCTs, randomized evaluations, trials, or experiments are the gold standard for impact evaluation due to their ability to establish causality with minimal assumption. So the basic idea of RCTs is that participants are randomly assigned to a treatment group, so p is equal to 1, or a control group where p is equal to 0, so they don't receive the treatment. And then this setup allows the average treatment effect, the ATE, to be estimated by comparing outcomes between the two groups. The assumption is that we have perfect compliance with assigned treatment, and then it can be relaxed later. And so in terms of the advantages of RCTs, it establishes a reliable comparison group or counterfactual. It has a tailored design. It answers specific research questions by controlling timing, location, and implementation. The limitation is that results are context-specific and may not generalize. They also have few assumptions. It eliminates selection bias, and it's simpler and more transparent than quasi-experimental methods. RCTs also have prospective evaluation. They're designed in advance, enabling targeted data collection and collaboration. The challenge is long-term results that need extended timelines. Now, in terms of these steps in random assignment, first you define those eligible for a program. Second, you randomly assign who's in the treatment group and who's in the control group among the eligible participants. Third, you implement the intervention only for the treatment group individuals. And then finally, you compare or survey outcomes for those in the treatment group or who got the program and comparison groups who got no program. Now, in terms of the limitations of RCTs, they're not suitable for macro-level outcomes, for example, exchange rates, freedom of the press, etc., and also situations with general equilibrium effects, for example, market-wide price changes, unless markets are isolated. And then in terms of ethical considerations, we have to take a look at the Belmont principles for research. First is respect for persons. Get informed consent from the participants. And then beneficence. You need to balance the risks and the benefits of the research. And then finally justice. The people or group who take the risk should be those who benefit. So the research may need approval from institutional review boards, etc. as well. And now, what are the benefits of RCTs? Well, they have a high societal impact. Evidence can lead to scaling beneficial programs or stopping harmful ones, and the causal clarity enhances ethical justification by maximizing research benefits. When setting up a randomized evaluation, we need the target population, the broad group of interest, for example, rural farmers. Then we need the evaluation sample, which is the subset selected for the study, for example, all female rural farmers. And then we have random assignment. The sample is randomly split into the treatment group, who receives the intervention, and then the control group who doesn't receive the intervention. And then finally we have attrition. And so how does randomization solve the evaluation problem? Well, we have balanced groups. Randomization ensures the treatment and control groups are statistically identical in both observed and unobserved characteristics. So observed characteristics could be gender, education, and unobserved characteristics could be motivation. And therefore, any post-intervention outcome differences can be attributed to the treatment. And so we want to estimate the ATE, which is the difference between Y1 and Y0, and ATT, which is the difference between Y1 and Y0, given that P is equal to 1. Estimating ATE, the average treatment effect, under perfect compliance means that we assume that everyone follows their random assignment. T denotes random assignment to the treatment, and so if they're assigned to the treatment, T is equal to 1, therefore they participate, so P is equal to 1. And then if they're assigned to the control, then T is equal to 0, therefore they don't participate, so P is equal to 0. And then we estimate the average treatment effect, which is equal to the estimated value of y given that t is equal to 1 minus the expected value of y given that t is equal to 0. And so the expected value of y given t is equal to 1 estimates y1, so they are treated, and then y given that t is equal to 0 estimates y0, meaning they are not treated. Another method of randomization is a two-stage randomization. And this is common in the medical field or job training RCTs. So the first step is that individuals self-select into applying for the program. So D is the desire to participate, and if D is equal to 1, they participate, and if D is equal to 0, they do not want to participate. And then the second step is that applicants are randomly assigned to treatment, so T is equal to 1, or control, so T is equal to 0. And so the key features are that it estimates the average treatment effect on the treated, and not the average treatment effect, since only those interested are randomized. There's also high compliance since participants already opted in. Now, what if some people assigned to the treatment choose not to participate? Well, not everyone who's randomly assigned to the treatment group chooses to participate. And so this creates three subgroups. First is the control group, where t is equal to 0, and this provides the estimate of y0, the baseline outcome without the treatment. And then the second group is the treatment compliers. These are assigned to the treatment and they choose to participate. So t is equal to 1, d is equal to 1, and p is equal to 1. This provides the estimate of y1 given that p is equal to 1. And then we have the treatment non-compliers, where d is equal to 0, t is equal to 0, and p is equal to 0. This provides the estimate of y0 given that p is equal to 0. And so we can still estimate the ATT if we assume that all the people assigned to the control group don't participate in the treatment. Under random assignment, non-compliers in the treatment group, where t is equal to 1 but p is equal to 0, can proxy for the estimate of y0 given that p is equal to 1, assuming their characteristics mirror compliers. And so we calculate the ATT as follows. The ATT is equal to the difference of y given that t is equal to 1 minus y given that t is equal to 0 divided by p given that t is equal to 1. And this is the proportion of people in the treatment group who take the treatment. But now, what is the intention to treat effect? Well, this measures the impact of being offered the treatment regardless of participation. It reflects real-world scenarios where take-up is imperfect, and so the ITT is equal to the expected value of y given that t is equal to 1 minus the expected value of y given that t is equal to 0. Therefore, it's the difference in outcomes between all assigned to treatment, so t is equal to 1 versus the control, t is equal to 0. And you should know that the intention to treat effect is less than or equal to the ATT, the average treatment effect on the treated, as the ITT dilutes the effect by including non-compliers. But now let's take a look at the methods of randomization. So we have the lottery, we have the phase-in design, and the encouragement design. The lottery is simple randomization. It randomly assigns units to the treatment group or the control group. It's best for small-scale or pilot programs, oversubscribed programs with excess demand, and long-term impact studies where the control group remains untreated. The challenges here are high attrition in the control group, since there's no incentive to stay, and ethical concerns. The control group never receives the treatment. And then we have a phase-in design, where everyone eventually receives the treatment, but rollout is staggered. This is best for universal programs with logistical or financial constraints, and maintaining control group cooperation. Participants know they'll receive the treatment later. The challenges here are that the control group disappears over time. This limits long-term measurement and anticipation effects. For example, they won't buy something new if a free one is coming. And then we have the encouragement design. This randomly encourages subsets to participate, for example, via adverts. This is best for undersubscribed programs or programs with high application effort. The key assumption here is monotonicity. The encouragement affects everyone in the same direction. And so we have a local average treatment effect, LATE, for compliers, so those who participate only if encouraged. And so the local average treatment effect, LATE, measures the impact only on compliers, so those who respond to encouragement, not the ATE, the entire population, or the ATT, all participants. And so monotonicity violation is when the encouragement discourages some people. For example, lower than expected benefits reduce participation, and so the LATE fails. We can also use regression analysis to estimate treatment effects. And the advantages here are that it tests statistical significance of effects, it controls for covariates, so it improves precision, and it estimates heterogeneous effects, for example, impacts by gender. For example, y would equal to a0 plus bt plus u. So if t is equal to p, there's perfect compliance, and beta estimates the ATE, and it requires randomization to ensure that t is uncorrelated with u. Now let's talk about conducting an impact evaluation and pre-analysis plans. Well, the steps to consider when planning an intervention is first, clarifying what the program and the outcome variables of interest are, formulating a theory of change to refine the evaluation questions, depicting the theory of change in a results chain, formulating specific hypotheses for the impact evaluation, selecting performance indicators for monitoring and evaluation, then identifying relevant data sources and data collection methods, then establishing the implementation process of your intervention, then describing the estimation strategy of your data analysis, and finally discussing possible threats to internal and external validity of the RCT study and how the study will try to mitigate these effects. And so the first step is defining the program and outcomes of interest. So here you'd clarify the project, program, or policy being evaluated, identify the outcome variables of interest in consultation with stakeholders, policymakers, program managers, beneficiaries, etc., and note that programs may evolve and outcomes can vary by location and time. The outcomes may be immediate or long-term, intended or unintended. And then step 2 is developing a theory of change. Here you formulate how the program is expected to influence the outcomes. The theory of change should outline the causal pathway from program activities to desired results. It helps refine evaluation questions, identify moderators or mediators, and align indicators. It should ideally be created during program design and informed by similar programs. And then the third step is depicting the theory of change in a results chain. And so you'd have inputs, which are the project's resources like funds, staff, or equipment, and then activities, which are the actions taken with the inputs, for example, training or construction, the outputs, which are the direct products, for example, schools built or nurses trained, and then you'd have the outcomes, which are the beneficiary level changes, or what's changed by the project, for example, improved learning or reduced illness. And then finally, we'd have the impact, the causal effect of the program on the final outcome, the difference in the outcome of interest between those who were exposed to the policy or intervention and those who weren't. Step 4 is formulating the specific hypotheses. So you define clear, measurable outcomes, short and long term. You specify the timing and potential variations across subpopulations. And you ensure the hypotheses are testable and aligned with the results chain. And then finally, step 5 is selecting performance indicators for monitoring and evaluation. And we should know outcome variables aren't always easy to measure. So selecting clear performance indicators help track both program progress and results. The SMART criteria for indicators is that they are specific, so simple, communicable, and easily understood. Measurable, so they must be quantifiable or observable. Achievable, so they should be sensitive to changes during the project's lifespan. Relevant, so they must provide meaningful data for decision making, and they should be time-bound, so the progress should be tracked at defined intervals. Now, what is a pre-analysis plan, a PAP? Well, a pre-analysis plan is a detailed step-by-step guide written before analyzing or collecting data. It outlines how data will be analyzed to prevent issues like data mining, so cherry-picking results, and specification searching, tweaking methods to get desired outcomes. And this is crucial for studies with many possible outcomes. Now, why are pre-analysis plans important? Well, it improves questionnaire design. It ensures all necessary variables are measured and aligned with the research questions. It streamlines analysis, providing a clear roadmap and making data analysis faster and easier. It also enhances credibility. It reduces bias by committing to methods upfront. Now let's take a look at the key sections in a pre-analysis plan. Well, we have the description of the sample to be used in the study, how the sample was obtained, expected size, randomization method, and balance tests. Then we have the key data sources, so surveys, administrative data, or other sources. And then we have the hypothesis and causal chain. It should specify the key outcomes of interest, the steps in the causal chain to be measured, and subgroup analyses. Then we have the variable construction, handling logs, missing data, outliers, etc. Then the treatment effect model, the exact regression equation to be estimated, for example, difference in differences, controls, and standard errors. And then we have multiple hypothesis testing, methods to address many outcomes, for example, aggregating variables into indices. Then we have survey attrition, plans to check and adjust for selective dropout. Then we have to deal with outcomes with limited variation, so excluding outcomes with no variation, for example, 95% with the same response, and this is to reduce noise. And then you might have a pre-specified model, so theoretical models you're testing. And here we need to ensure that all needed data is collected. Now let's take a look at practical advice for implementing randomized evaluations. So first we take a look at causal inference and counterfactuals. So the causal impact of a program P on an outcome Y is the difference between outcomes with and without the program. So the difference between Y given P is equal to 1 and Y given P is equal to 0. And so the counterfactual Y given P is equal to 0 represents what would have happened without the program and must be estimated using a comparison group similar to the treatment group. And so randomized controlled trials, RCTs, randomly assign participants to the treatment group P is equal to 1 or the control P is equal to 0, ensuring the groups are similar except for the treatment. And this gives credible estimates for ATE and ATT. And now we take a look at the common problems and solutions in RCTs. Well, we may have contamination bias. This is where the control group may access similar programs. And so the solution here is to use instrumental variable methods with random assignment as the instrument and track contamination. Another problem we may have is dropout. Participants may leave the program early. Well, the solution to this is to treat dropouts as untreated and use the instrumental variables. Then conduct intent to treat analysis, ITT analysis, defining treatment as starting the program. Then compare bounds. Lower bound includes dropouts, upper bound excludes them. Another problem is sample attrition. Participants may leave the study, for example, due to migration, and non-random attrition biases estimates. We also have randomization bias. This is where behavior changes due to awareness of the evaluation. For example, we may have Hawthorne effects, where the treatment group works harder, or we may have John Henry effects with control group estimates. Another problem we may face in RCTs is spillovers. This is where treatment effects may affect the control group, especially in proximity. Solutions could be to randomize at the community level if spillovers are local, and estimate spillovers explicitly. Now let's take a look at the methods of randomization once again. So we should use the lottery method when funds are insufficient to treat all eligibles, and when it's ethically justified not to treat some. The advantages of the lottery method is that it's accepted as fair, it's easily understood, and randomization can be done publicly. The disadvantages here though is that the control group may not cooperate, and differential attrition. In terms of the phase-in method, we should use this when the program slowly expands over time and if everyone gets treated eventually. The advantages here are that it's easy to explain, the control group may be more likely to cooperate, and is politically feasible. Disadvantages are that anticipation of future treatment may affect behavior, and it's hard to measure long-term impact. And then with the encouragement design method, we should use it when the program can't exclude anyone. Advantages are that it can be used when exclusion is not possible, so everyone is included. Disadvantages are that it applies only to those who respond to the incentive, and the incentive may have no effect. And so lotteries are often the best method when feasible. And to address concerns about deserving individuals, a hybrid approach can be used. We can divide the population into the clearly deserving, so all treated, and then the somewhat deserving, so treatment is decided by lottery, and the not deserving, so they're excluded. This allows for randomization for the middle group. And then phase-in designs require the order of the implementation to be random to avoid systematic differences between early and late groups. And then encouragement designs, for example, providing random encouragement to join a program, are valid only if the encouragement itself has no direct effect on the outcome. It can only have an indirect effect through program participation. And then in terms of the levels of randomization, we have individual level randomization, and this is usually preferred as it provides a larger effective sample size. And then we have group level or cluster randomization, and this is sometimes necessary, for example, for school level interventions or due to political constraints. And so group level randomization requires a larger sample size to achieve the same statistical power. And it's better if there are individual level externalities or spillover effects. And it can increase cooperation and reduce interaction between the treatment and control units. Now let's take a look at some practical advice on implementation. So in terms of pilot programs, you start with a small pilot to learn about implementation and convince wary participants of the trial's ethics and value. And then in terms of monitoring implementation, researchers must actively monitor the program's implementation and data collection from the start. And then in terms of multiple treatments, it can be useful to test multiple program variants simultaneously. For example, 1 control and 3 treatment groups. And then we could look at multiple experiments. Conducting different, unrelated experiments on the same sample can be cost-effective, provided the treatments don't interact. If interaction is of interest and is expected, an independent, cross-cutting design can be used. Now let's take a look at the importance of baseline data. So baseline data is data collected before the program is implemented or even announced. Collecting data after the program has started greatly diminishes its value, as informing people about a program can change their behavior. The advantages of baseline data is that it provides unaffected control variables to increase the precision of impact estimates. It allows for analysis of subgroup effects. It enables researchers to check for balance and verify that randomization was done correctly, and improves the quality of subsequent data by providing learning experience. Now let's take a look at sample size, power, and the minimum detectable effect. So first let's talk about the importance of sample size. Well, a larger sample size leads to more precise estimates. A small sample, for example 1 child from treatment and control groups, is highly susceptible to random variation, potentially showing a negative program effect even if the true effect is positive. While measuring the entire population is ideal, larger sample sizes incur higher costs, creating a need for a method to determine the optimal size. In terms of hypothesis testing errors, we have a type 1 error, which is a false positive, rejecting a true null hypothesis, for example, concluding the program worked when it didn't, and its probability is denoted by A or alpha, the significance level. And then we have type 2 errors, a false negative. This is failing to reject a false null hypothesis, for example, concluding the program had no effect when it did. Its probability is denoted by beta. Now let's talk about defining power and its role in sample design. Well, the significance level, alpha, is the probability of making a type 1 error, and it's set by the researcher, usually 0.05. And then power is 1 minus beta. This is the probability of correctly rejecting a false null hypothesis, so essentially detecting a real effect. A common target for power is 0.8 or 80%. And so the goal is to choose a sample design, size, and allocation that achieves the desired level of power, for example 80%, for a given significance level, 5%, to test a specific null hypothesis, for example no average treatment effect. But now let's take a look at the factors affecting the power of a test. Well, first is the sample size, n. The larger the sample, the higher the power. Then we have the significance level, alpha. A smaller alpha, so stricter threshold for rejection, reduces power. And then we have the proportion treated, p. So power is affected by how the sample is split between the treatment and control groups. And then we have the variance of the outcome, the standard error squared. So higher variance in the data, not due to the program, reduces power. And so the simplest impact evaluation model is the regression, where y is equal to alpha plus beta multiplied by p, where p is equal to 1 for program participants and equal to 0 for non-participants, plus u, and u can be assumed to be uncorrelated across the individuals. And so the variance of the OLS estimate for b is equal to 1 divided by p bar multiplied by 1 minus p bar multiplied by the variance divided by n. where p bar is the proportion of the sample that participated. Now, what is the minimum detectable effect size, MDES? Well, the MDES is the smallest true program effect, beta, that a study can detect with a specified power and significance level. It's derived from the distributions of the estimator under the null and alternative hypothesis, and it's effectively the sum of the t-values multiplied by the product of the standard error multiplied by the OLS estimate of b. Now let's take a look at other estimators and difference in difference estimators. So now we take a look at non-randomized impact evaluation. So here the focus shifts from randomized evaluations to methods used when random assignment isn't possible. A common scenario is evaluating programs that already exist, where participation isn't random. And this non-randomness happens because A, the program communities aren't randomly chosen, or B, program participants aren't randomly assigned. And so the three primary methods for estimating program impacts in these contexts is first, the before-after estimator, or two, the cross-section estimator, or the difference in differences estimator. And so the before-after estimator estimates a program's impact by comparing the outcomes after the program started with the outcomes before it started. For example, maize yield was 1,000 kilograms per hectare before the program versus 1,200 kilograms per hectare after the program. And so the calculated impact is 200 kilograms per hectare. But then the core problem is that the before-after estimator can mistakenly attribute changes over time to the program when they were actually caused by other external factors, for example, changes in weather. And so the two cases here could be that a drought in the program year would make the estimated impact less than the true effect, or case B, recovery from a drought in the previous year would make the estimated impact greater than the true effect. But then we have the cross-section estimator. This calculates a program's impact by comparing outcomes for participants and non-participants at a single point in time after the program is started. It uses the non-participants as a comparison group to represent the counterfactual, what would have happened to the participants without the program. The data requirements here are minimal. Only a single round of data collection is needed after the program begins. The core problem here is selection bias. Participants and non-participants are likely to differ from each other in systematic ways, unobserved differences that also affect the outcome. The estimator mistakenly attributes these pre-existing differences to the program's effect. Examples of the selection bias could be that in scenario A, more productive farmers self-select into the program because they're more confident that they can repay the loan. And so their higher yield is due to their inherent productivity, not just the loan. Scenario B is where the program might target farmers with poorer quality land who need more fertilizer. Their lower baseline potential could mean the program's true effect is greater than the estimate suggests, or it could introduce bias in either direction. Now we take a look at the difference in differences DID estimator. While this measures a program's impact by comparing the change in outcomes over time for the treatment group, the participants, to the change in outcomes over time for the comparison group, the non-participants. So it combines the before-after and cross-sectional approaches. And so the DID is equal to the change in the treatment group minus the change in the comparison group. And so the change in the treatment group could be, for example, the difference between the ones enrolled after and the ones enrolled before. And this is similar to the before-after estimate. And then the change in the comparison group could be the ones non-enrolled after minus the non-enrolled before. And you'll notice that the cross-sectional estimate looks at the difference between the ones enrolled after and the non-enrolled after. And we should know that the DID method relies on the common trend assumption. This assumes that in the absence of the program, the outcomes for the treatment and comparison groups would have followed parallel paths over time. This allows the trend of the comparison group to be used as a valid counterfactual for what would have happened to the treatment group without the program. And so difference in differences controls for two main sources of bias. The first is time invariant differences between groups, for example, inherent land quality, farmer skill, etc. These are removed by comparing changes within each group, and also common time trends affecting all groups, for example, drought recovery. These are removed by subtracting the comparison group's change from the treatment group's change. And so for an example of the DID, for the people who were enrolled, before farmers got 1,000 kilograms per hectare, and after they got 1,150 kilograms per hectare. And so there's a plus 150 kilograms per hectare change. And for the ones that were not enrolled, before they got 900 kilograms per hectare, and after they got 1,000 kilograms per hectare. And so there's a plus 100 kilogram per hectare change. And so we can see that the general trend is that there's a recovery from a drought regardless of whether or not you were enrolled. And so the DID impact is equal to 150, the change in the treatment group, minus 100, the change in the comparison group. And this equals to 50 kilograms per hectare. And so this is the program's true effect. And so in terms of its advantages over other methods, DID provides a more plausible estimate of impact than the cross-section estimator, which ignores selection bias, or the before-after estimator, which ignores external time trends. So it accounts for both pre-existing group differences and common shocks. Now we move on to regression discontinuity design, RDD. So RDD is an evaluation method used when a program's eligibility is determined by whether a continuous variable, for example income, test score, poverty index, etc., falls above or below a specific threshold. It's ideal for estimating the causal effect of a program or intervention in these scenarios. The design leverages the discontinuous change in treatment status at the eligibility cutoff. The fundamental assumption is that individuals just above and just below the threshold are virtually identical in all characteristics except for their treatment status. Therefore, any sharp difference in their outcomes near the cutoff can be attributed to the program's effect. And so you'd have the post-test score on the y-axis and the pre-test score on the x-axis. And then on the x-axis, you'd have the non-treated to the left of the cutoff and the treated individuals to the right of the cutoff. And so we see that there's a sharp difference or parallel shift between the observations. This vertical shift is the treatment effect, and then the counterfactual is the line if it had not shifted. And so the RDD acts like a local randomized controlled trial, or RCT, around the cutoff. The outcome for the untreated individuals just below the threshold is used as the counterfactual for the treated individuals just above the threshold, or vice versa, depending on the eligibility rule. For the design to be valid, individuals must not be able to precisely manipulate their score to control their eligibility around the threshold, ensuring local randomization. Now let's take a look at sharp versus fuzzy RDDs. Now a sharp RDD is where the treatment assignment is a strict deterministic rule. All units on one side of the cutoff, for example Zi being bigger than Z0, Z0 being the threshold, are treated. And all units on the other side, so Zi being less than or equal to 0, aren't treated. And here there's full compliance with the assignment rule and no contamination of the treatment and control groups. The impact is estimated by simply comparing the average outcomes of individuals just above and just below the cutoff threshold. But then the assumption here is that while the assignment variable Z may be correlated with the outcome, individuals very close to the threshold Z0 are assumed to be similar in all other aspects. This creates a scenario similar to a local randomized experiment near the cutoff, especially if people can't manipulate their z-score, for example age. But then we have a fuzzy RDD. This is when treatment assignment is probabilistic and not deterministic. Being on one side of the cutoff increases the likelihood of treatment but doesn't guarantee it. Conversely, being on the other side makes treatment less likely but still possible. There is non-compliance with the theoretical assignment rule. This leads to contamination. The treatment group contains some untreated individuals and the control group contains some treated individuals. And so the implication here is that a simple comparison of average outcomes across the cutoff is biased because the groups aren't pure. The fuzzy RDD requires more complex statistical methods like instrumental variables to isolate the effect of the treatment itself from the mere probability of assignment. But the identifying assumption for both sharp and fuzzy RDD is that individuals immediately on either side of the eligibility threshold are comparable. This allows the discontinuity in the probability of treatment, which is sharp in one case and fuzzy in the other, to be used to identify the causal effect of the treatment. But now, how do we go about checking the validity of an RDD? Here we see the importance of covariate balance. So the RDD method relies on the assumption that individuals immediately on either side of the cutoff are comparable. This assumption is tested by examining the distribution of observed baseline characteristics, for example age, income, prior test scores, etc., around the cutoff. Researchers then report and compare the means of these covariates for groups just above and just below the threshold. And a statistically significant difference in these means is a red flag. If covariants aren't balanced, it suggests that individuals may have been able to manipulate their score on the assignment variable Z to gain eligibility. For example, taking a test until they pass, violating the local randomization assumption. But now let's take a look at the limitations of RDD. While it's difficult to generalize RDD results, RDD estimates the local average treatment effect late, so it estimates the impact only for units or people whose scores are very close to the cutoff. RDD also has lower statistical power. The analysis focuses only on a narrow window around the cutoff. The effective sample size is smaller compared to methods that use the entire dataset. This makes it more difficult to detect a statistically significant effect if one exists, unless the effect is very large or a very large sample is available near the cutoff. RDD also has larger data requirements. To overcome the statistical power problem and precisely estimate the effect, RDD requires a large number of observations densely distributed around the cutoff point. Now we move on to propensity score matching. So matching methods are used in impact evaluation to estimate causal effects without randomized experiments. The goal here is to create an artificial control group by matching treated and untreated units with similar observable characteristics. The assumption here is that program participation is random, conditional on observed variables or characteristics, Z. Now the two main types of propensity score matching PSM estimators are the cross-sectional PSM, which requires only one period of data, and then we have the difference in differences PSM, which uses panel data. And so the basic concept of matching is that we find a non-treated unit similar to each treated unit on observed characteristics. For example, evaluating a job training program, and so you compare wages of treated versus non-treated individuals with similar education, experience, etc. But then we have the dimensionality problem. If many variables or characteristics matter, exact matching becomes impossible. The data needed for PSM is observational or non-experimental data with information on outcomes, treatment status, and observable characteristics. Now, propensity score matching resolves the dimensionality problem by matching on the propensity score. So PRZ, the propensity score, is equal to the probability of participating in the program given observed characteristics. So the probability of P is equal to 1 given Z. Once we condition on this probability, treatment P is independent of potential outcomes Y1 and Y0. So instead of matching on many variables, we match on one score. Now, when estimating the ATT with propensity score matching, we compute the propensity scores via a logit or probit model. Then for each treated person, we find a non-treated person with a similar score. Then we calculate individual outcome differences, so Y1 minus Y0, and then the mean of these differences is equal to the ATT. Now, what are the key assumptions of propensity score matching? Well, we need conditional independence. Once we control for observables, Z, treatment becomes random. And then we need a common support. There must be both treated and untreated individuals for all levels of Z, so matches exist. And then the propensity model must also be correctly specified. Now let's take a look at these steps of implementing propensity score matching. Well, first you collect data on treated and untreated individuals. Then second, you estimate participation probability, so the propensity score. Then you restrict the sample to the common support. Then you match the treated with similar untreated units. And then finally, you compare average outcomes and you estimate the program impact. Now let's take a look at the different matching estimators. Well, we have nearest neighbor matching. So here you match to the closest score. The weakness here though is that if no control unit has a very similar score, the matches can be poor quality, leading to bias, and it may increase variance if only one neighbor is used. Then we have the caliper or radius matching, and here you match only within a set distance or epsilon. The weakness here though is that if calipers are too small, many treated units may have no matches, and this reduces the sample size. But then if it's too large, bias increases because there's too much matching. Then we have the interval matching. Here you match within score intervals, for example 0.1 bands. The weakness here though is that there may be a loss of precision. Broad intervals can mask differences, and there may be residual bias and reduced efficiency. And then finally, we also have kernel matching. Here we get the weighted average of all non-treated units based on distance and scores. This one risks bias from including distant controls and depends heavily on bandwidth choice. Now let's take a look at the limitations of propensity score matching. Well, it's very data hungry. It needs large samples and detailed covariates. There may also be a lack of common support. Some treated units may have no comparable controls. There's also unobserved heterogeneity. Matching can only be done on observed characteristics or variables, so unobserved differences can bias estimates, and the assumption that no selection bias has occurred stemming from the unobserved characteristics can't be tested.